Those giant screens towering over Times Square aren't what you think they are. They're essentially millions of Lego bricks lighting up the sky. Yeah, you heard that right. That massive display blasting advertisements 24/7 isn't one solid piece. It's actually thousands of small tiles, each about the size of a hardcover book, snapped together like the world's most expensive building block set. And here's the kicker. Each one of those tiles is hand-assembled, waterproofed with black goo, and calibrated by a robot camera to make sure every single pixel matches perfectly. Welcome to the insane world of digital billboard manufacturing. Let's talk numbers for a second. The giant billboard in Times Square, it uses over 12 million LEDs. 12 million! That's more LEDs than there are people in New York City. And every single one of those tiny lights had to be soldered onto a circuit board by hand. Well, mostly by machines, but you get the idea. The process is so precise, so ridiculously complex, that one mistake could ruin an entire module. So how do they actually make these things? The module, where it all begins. Everything starts with a small square tile, usually measuring around 320 by 160 millimeters. That's about 12.6 by 6.3 inches for those of us who don't speak metric. This is the module, and it's the basic building block of every digital billboard you've ever seen. Think of it like a single Lego brick, except instead of colorful plastic, it's packed with hundreds of tiny LEDs, resistors, capacitors, and integrated circuits that control the whole light show. The manufacturing process begins with the PCB, the printed circuit board. This green board arrives at the factory completely blank, like a canvas waiting for an artist. Workers slap identification labels on each board for quality control and tracking. Then comes the fun part, applying solder paste. Now, solder paste isn't your regular paste, it's a mixture of tiny solder particles and flux, and it gets applied to specific spots on the circuit board using an automatic stencil machine. Picture a giant mechanical squeegee spreading this metallic goop across the board with surgical precision. The paste acts like temporary glue, holding components in place before the real magic happens. Next up, robots get to work. Surface mount technology machines, SMT machines for short, start placing components onto the board at lightning speed. We're talking resistors, capacitors, integrated circuits, power interfaces, all the electronic guts that make the LEDs work. These machines are so fast and accurate that they can place hundreds of components per minute without making a mistake. Try doing that with your hands. But here's where things get intense. The boards loaded with components enter a reflow oven, basically a high-tech, easy-bake oven on steroids. The temperature ramps up gradually to about 150 to 180 degrees Celsius, then cranks up even higher to 235 to 250 degrees Celsius. At this peak temperature, which lasts only 20 to 40 seconds, the solder paste melts and fuses all the components to the board permanently. The temperature control has to be insanely precise. Too hot and you'll fry the components. Too cold and the solder won't bond properly. After soldering, the boards cool down slowly to prevent thermal stress that could crack the connections. Now here's the part that'll blow your mind. They do this twice. After the first round of reflow soldering secures the electronic components, workers apply another layer of solder paste, this time on the lamp surface where the actual LEDs will go. Then comes the LED placement. Hundreds of tiny LED lamp beads get mounted onto the board. Each LED is a miniature light source containing red, green, and blue diodes that can mix together to create millions of colors. The board goes back into the reflow oven for a second time. This second pass solidifies the LEDs in place, creating both a mechanical bond and an electrical connection. Every single LED must be perfectly aligned and securely attached because once these modules are 50 feet in the air on a billboard, you can't exactly reach up and fix a loose bulb. After cooling, each module gets rigorously tested. Power on testing, brightness checks, color calibration. If a module doesn't meet standards, it gets marked for rework or rejected completely. Quality control is everything in this business because one bad module can create a dark spot on a billboard that ruins the entire display. Waterproofing, the black goo that saves everything. So you've got this module packed with sensitive electronics and hundreds of LEDs. Great. Now imagine mounting it on a billboard where it'll face rain, snow, dust, scorching heat, and freezing cold, sometimes all in the same week. Without protection, that module would die faster than your phone battery on 1%. Enter the black goo. Officially, it's called silicone potting compound, but black goo sounds way cooler. This stuff is basically the superhero cape for outdoor electronics. Potting compound is a two-part liquid mixture that looks innocent enough when you pour it. Part A and Part B get mixed together in a precise ratio, usually 1:1 by weight. Once mixed, you've got a limited window to work with it before it starts curing. This is called the pot life, and for typical silicone compounds, it's about 45 minutes at room temperature. Workers, or automated dispensing machines, pour this silicone mixture directly over the LED module's electronics. The liquid is designed to have low viscosity and good flowability, meaning it seeps into every tiny gap and crevice, coating every component. The silicone completely encapsulates the circuit board, creating a protective barrier between the sensitive electronics and the brutal outside world. Why silicone specifically? Because it has some ridiculously good properties. First, it's incredibly flexible, even after it cures into a solid rubber-like material. This flexibility means it can handle vibrations and mechanical stress without cracking. Second, it's waterproof and weatherproof. Rain, humidity, dust, the silicone blocks it all. Third, it can handle extreme temperatures, staying flexible and protective anywhere from -60 to +250 degrees Celsius. And fourth, it conducts heat away from the LEDs, preventing them from overheating and burning out. The potting compound cures either at room temperature over several hours or gets accelerated with heat. Once fully cured, it forms a tough, rubbery coating that essentially mummifies the electronics. Even if water somehow gets on the module, it can't get to the electronics. But wait, there's more. For outdoor modules, the ones destined for billboards exposed to the elements, manufacturers add extra layers of protection. After potting, the modules get a conformal coating, which is like a thin protective paint layer. Then they install a bottom shell or housing made from durable materials with ventilation slots to dissipate heat while keeping water out. Some modules even get a mask installed over the LEDs to protect them physically and reduce glare from sunlight, making the display visible even in bright daylight. This multi-layer waterproofing approach is what allows digital billboards to stay lit 24/7, 365 days a year in any weather condition imaginable. Assembly: building a screen as big as a building. You've got thousands of these waterproof modules ready to go. Now comes the really cool part, putting them all together to create a screen the size of a building. Digital billboards use a modular design for good reason. It's way easier to ship, install, and maintain. Instead of trying to manufacture one gigantic screen in a factory and somehow transport it to Times Square, manufacturers build the billboard in sections that snap together on site. Each module clicks into a cabinet or frame using a latch assembly system. These aren't your wimpy plastic clips. We're talking heavy-duty mechanical latches that lock each module firmly in place while still allowing it to be individually removed from either the front or back of the display if it needs service. The modules slide into mounting channels on the frame, and the latch assembly ensures they're perfectly aligned with their neighbors. Here's where the Lego comparison really hits home. Just like Lego bricks, each module has standardized connection points. The modules connect to each other through power and data cables. Signal cables and power interfaces run between modules, linking them into a unified display system. Thousands of these connections have to be made, and every single one must be secure and weatherproof. For a typical large digital billboard, let's say 14 feet high by 48 feet wide, you might need over 10,000 individual modules. That's 10,000 pieces that have to fit together perfectly with zero gaps between them to create one seamless image. The precision required is insane. If the LEDs are more than a quarter of an LED width out of alignment between modules, installers have to adjust until everything lines up. The assembly happens in stages. Steel beams form the backbone, a massive framework engineered to withstand high winds and support tons of weight. These beams are measured, cut, welded, and bolted together to create a structure strong enough to hold the display. Then comes the real show, Crane Day. Installing a digital billboard requires massive cranes, sometimes 150-ton cranes capable of lifting the display sections high into the air and positioning them with pinpoint accuracy. In windy conditions, lifting these displays becomes especially tricky because the flat LED panels act like giant sails catching the wind. The crane operators and ground crew coordinate carefully, using ropes and spotters to keep everything steady and aligned as they hoist sections into place and bolt them to the steel frame. Some displays get assembled on the ground first, then lifted as complete sections. Others get built piece by piece while already mounted on the structure. Either way, it's a carefully choreographed dance involving specialized crews, expensive equipment, and split-second timing. Calibration, making 12 million pixels match perfectly. All right, your billboard is assembled. Thousands of modules, millions of LEDs, all connected and powered up. You flip the switch and it looks terrible. Some pixels are brighter than others. The colors don't match. One section looks bluish while another looks greenish. Welcome to the calibration nightmare. Here's the problem. Every single LED is slightly different. Manufacturing variability means that even LEDs from the same batch will output different amounts of light when given the same electrical current. Multiply this by 12 million LEDs and you've got a visual disaster. Without calibration, your expensive billboard looks like a patchwork quilt of mismatched colors and brightness levels. The solution? Robot cameras and some seriously smart software. The calibration process starts with a professional-grade camera positioned in front of the display. This isn't your smartphone camera, it's a specialized device that can measure the exact light output and color characteristics of individual pixels. The camera scans the entire screen, collecting pixel-level data on brightness and color for every single LED. This is where the magic happens. The calibration software analyzes all that data and compares each pixel's output to the ideal target values. Then it generates correction factors for each individual LED. If one LED is outputting too much red, the system notes to reduce the current to that red diode. If another LED is too dim, the system increases its current. These correction values get uploaded to the receiving cards, the electronic controllers built into each module that drive the LEDs. The result? A calibration map that tells every single LED exactly how much current it should receive to produce the correct amount of light. When this calibration data is applied, suddenly the patchwork becomes a uniform, smooth image with perfect color accuracy across the entire display. Calibration isn't just about initial setup either. LEDs age over time, and their brightness and color gradually shift. Environmental factors like heat exposure and component aging can introduce new inconsistencies. That's why many high-end digital billboards get recalibrated periodically to maintain optimal image quality throughout their lifetime. Some modern systems even include automatic calibration features that use built-in sensors to monitor and adjust LED performance in real time, keeping the display looking perfect without human intervention. The final product. So there you have it. Those massive digital billboards aren't single screens. They're thousands of carefully crafted modules, each one soldered by machines, waterproofed with silicone goo, snapped together like Lego bricks, and calibrated by robot cameras to create a flawless image visible from blocks away. The next time you see a digital billboard, remember, you're looking at millions of individual LEDs, thousands of individual modules, hundreds of pounds of steel framework, miles of cables, and countless hours of engineering and assembly, all working together to sell you a burger or a new phone. Pretty wild when you think about it. From factory floor to city skyline, digital billboards represent some of the most complex, large-scale electronics manufacturing in the world. And it all starts with one small tile, carefully assembled, one LED at a time. There yet, let's ride the assembly line, the birth of the body where heat meets shape. Before light can exist, it needs a home. That home, the LED bulb body. It's built to be strong, heat-resistant, and light-friendly. The process begins with placing the aluminum heat sink. That's not just any piece of metal. This is a vital part of the bulb that pulls away heat, keeping things cool even when the light's been on for hours. If it weren't there, the LED chip would burn out faster than you could say eco-friendly. After the heat sink is set, the base of the bulb starts taking shape through injection molding. Picture this: molten plastic. Hot and gooey, being injected into perfectly shaped molds. In seconds, it cools and hardens into the shell that will eventually hold all the inner components. It's fast, precise, and oddly satisfying to watch. Now it's starting to look like something real. Not just a blob of plastic and aluminum, but the beginning of something that will one day light up a room. The LED chip, tiny but mighty. At the heart of every LED bulb is a tiny yellow square, the LED chip. Don't let its size fool you. This is the real light maker. It's like the engine in a car or the CPU in a computer. Small but essential. The process kicks off with surface mount technology, or SMT, where these chips are delicately placed onto circuit boards with almost inhuman precision. Machines do this part because the chips are tiny. Like, really tiny. Trying to place them manually would be like threading a needle while blindfolded, with chopsticks. But for all the machine magic, there's still a human touch involved. Skilled workers step into solder wires onto the direct-on-board DOB LEDPCBS. It's a careful process. Each connection matters. A single weak joint and the bulb might never shine. And then come the IC drivers, little integrated circuits that control how power flows through the bulb. These are separated, sorted, and soldered onto the LEDPCBS, again by hand. Not because machines can't do it, but because these drivers are delicate, and sometimes machines just don't have the finesse. Some LED bulbs are compact, with IC drivers so tightly packed that assembling them by hand is the only option. Add to that certain sockets like the B22, which require hand assembly because automated tools just can't handle the design. It's a blend of automation and craftsmanship that keeps the process flowing. The driver, invisible but essential. Ever wonder how a bulb handles the electricity straight from your wall outlet? That's where the driver comes in. It's the silent workhorse hidden in the base, making sure everything runs smoothly from the moment power hits the socket. Tucked away inside the bulb's foundation is a small but essential circuit board that acts like a translator in taking the high-voltage alternating current, AC, that flows through household wiring and converting it into the low-voltage, steady direct current, DC, that the LED chip requires to shine bright without burning out. Without this component, flipping the switch wouldn't do anything but send raw voltage to a chip that's just not built for it. The journey of the driver begins with delicate precision. First, there's the soldering. Wires must be connected to just the right points, with clean joints that won't fail or under long hours of use. It's not simply about connecting parts, it's about ensuring those connections can handle surges, dips, and constant current flow. The driver board itself is mounted with care, often by hand, especially in more compact bulb designs where machines can't easily reach. These tight configurations demand human finesse, and the workers handling this part are incredibly skilled at making sure every lead is placed perfectly. Some LED bulbs operate with external or modular IC drivers, which are small integrated chips that regulate power flow. Others go the compact route, embedding the driver directly onto the main board. Both approaches have their advantages, but what they share is the absolute need for reliability. These components have to survive thousands of on-off cycles, endure voltage fluctuations, and keep the light steady without flickering or overheating. At this point in the production line, the bulb's internals are beginning to sink. It's a small symphony of micro-components now fully assembled, from chip to board, from wires to drivers. Electricity will enter at one end, travel through carefully soldered paths, get conditioned and converted by the driver, and finally reach the LED chip in just the right form. It's the technical heartbeat of the bulb. Yet, even with all this carefully crafted tech sealed inside, the bulb isn't quite finished. It still needs protection, polish, and proof that everything works the way it should. But for now, it stands as a fully wired promise, ready to turn energy into light with a single flip of a switch. The globe covering the light. With the engine ready and the wiring in place, the next step is to protect and shape the light. That's where the PC cover comes in, the dome-like cover that gives the bulb its familiar look and helps spread the light evenly. It's more than just a finishing touch, it's the diffuser, the final frontier between raw brightness and comfortable illumination. Depending on the design, this dome might be made from either plastic or glass, and each material brings its own character to the bulb. Plastic covers dominate most production lines due to their lightweight and durability, and the way they're made is nothing short of mesmerizing. The process begins with injection molding, molten plastic heated to the perfect temperature, then shot into molds that give it that smooth, curved shape. Once cooled, the covers are crystal clear or gently frosted, depending on the desired lighting effect. In some specialized production lines, the classic charm of glass is still used. It's a slower, more delicate process involving glass blowing, shaping the red-hot material into seamless domes before letting them cool into a pristine, transparent shell. Whether glass or plastic, each dome must be flawless. Any bubbles, warps, or scratches can affect how the light disperses. When ready, these domes are moved to the assembly line, where robotic arms take over. With sharp, precise movements, the arms grip each cover, rotate it gently, and lower it onto the bulb body. The alignment is spot on, no guesswork here, and the snap into place happens in one smooth, satisfying motion. But snapping alone isn't enough when the bulb will face years of heat and pressure. That's where adhesive comes in. A tiny bead of high-performance glue is applied at the base of the cover. It's clear, strong, and built to last. It ensures the dome doesn't shift, crack, or loosen over time. Once sealed, the bulb gets one step closer to completion. This entire process happens in seconds, repeated over and over across thousands of units per hour. And the result? A perfectly shaped light diffuser that not only protects the internals, but also softens and spreads the glow into something comfortable, familiar, and pleasant. The dome isn't just functional, it's what makes the bulb instantly recognizable on store shelves, and in every room it eventually lights up. Watching this part of the process unfold feels a bit like watching high-tech ballet, a dance between heat, precision, and polish. Semi-automatic magic, humans plus machines. Here's where things get really cool, the semi-automatic production line. It's part machine, part human, and all efficiency. Workers place the assembled PCB into the bulb base and feed it into the machine. It presses everything into place with just the right amount of force. The machine also leaves enough room for the PC cover to be added later. Spacing is everything here. Next comes the socket. Whether it's an E27 or B22 base, the socket is added and locked in. Some are screwed, some are clipped, but every one of them has to be snug. A loose socket is a safety hazard, and this process doesn't allow for mistakes. Even at this speed, rotating with thousands of bulbs moving per hour, every single one is handled with care. The aging rack, a wall of light. Every year, more than 200 million televisions are sold worldwide, finding their way into homes, offices, restaurants, and nearly every corner of daily life. The television has become more than just a screen to watch shows and movies. It is a window to the world, a hub for information, and a centerpiece of modern entertainment. But behind the sleek design, the vivid images, and the endless hours of content lies an extraordinary story of engineering, precision, and collaboration. Few people ever get the chance to see how these remarkable machines are brought to life. So today, the journey begins inside one of the largest television factories in the world, a place where machines and workers move in perfect synchronization to transform sheets of glass, tiny electronic components, and liquid crystals into the giant screens that dominate living rooms everywhere. This mega facility is truly a technological wonder in itself. Stretching across over 1 million square meters, it is a space the size of a small city. Within its vast walls, nearly 500,000 smart televisions are produced each year. The focus here is on large screens, the type of televisions that have become the centerpiece of modern households. Every corner of the factory is carefully designed for efficiency, where the hum of machinery blends with the swift, precise motions of skilled workers, creating a choreography that produces televisions on a massive scale. The sheer scale of the production floor can feel overwhelming at first, with conveyor belts running endlessly in different directions and machines rhythmically operating in perfect sequence. Specialized zones are set up for each stage of production, ensuring that every step flows smoothly into the next without delay. Automated vehicles glide silently across polished floors, transporting panels and components with clockwork accuracy. Workers dressed in matching uniforms move in unison like parts of a larger machine, each one focused on a task that contributes to the greater whole. Bright overhead lighting illuminates every corner, giving the impression of a space that never truly rests. Even during quieter moments, the atmosphere is charged with purpose, as though the factory itself breathes with life. Gigantic storage racks line the walls, stacked high with raw materials ready to be transformed into finished products. Robotic arms pivot with mechanical grace, lifting, rotating, and placing fragile parts without the slightest hesitation. The combination of human intuition and automated precision creates a balance that neither could achieve alone. Every workstation has been optimized for speed and accuracy, reducing wasted time and minimizing errors. Monitors display live production data, showing the output in real time and keeping the pace steady and consistent. Engineers keep a close eye on these figures, ready to make adjustments at a moment's notice to prevent bottlenecks. Safety is also a key priority here, with every worker trained to handle sensitive components carefully while following strict guidelines. The factory hums like a giant engine, where each sound, from the whir of cooling fans to the faint clicks of tools, is part of a larger symphony. Walking through the aisles, one can sense that the facility is designed not just for productivity, but for longevity, capable of meeting growing global demand for years to come. The heart of every modern television is its screen, and that is where the process begins. Unlike older, bulky models, today's televisions rely on liquid crystal display panels. These flat screens are not only thinner and lighter, but also capable of producing much brighter and more vibrant images. Compared to older cathode ray tube televisions, the difference is astounding. Modern flat screens bring clarity and color into homes that past generations could never have imagined. Yet, achieving such visual brilliance requires a manufacturing process that is both delicate and incredibly complex. The journey of creating a screen starts with materials that appear simple but demand extraordinary precision. Sheets of glass, polished until flawless, are carefully inspected to ensure they are free from even the smallest imperfection. These sheets form the foundation upon which billions of images will one day appear. The transition from thick, heavy tubes to razor-thin panels has completely changed not only how televisions look, but also how they fit into daily life. A screen that can hang like a picture frame on a wall is the result of decades of refinement in engineering. Unlike the fuzzy, curved glow of old cathode ray sets, These displays offer razor-sharp lines, vivid color contrasts, and a level of detail that feels almost lifelike. But the technology that allows such beauty to emerge is hidden beneath layers so fine they can barely be seen with the naked eye. Inside every screen is an orchestra of microscopic components working together, each one controlled with absolute accuracy. It is fascinating to realize that what looks like a simple surface is actually an intricate network, where millions of pixels are waiting to be lit in perfect harmony. The demand for bigger, brighter, and thinner televisions continues to push the limits of what manufacturers can achieve. Every advancement in screen technology represents years of experimentation and refinement, building upon earlier successes while overcoming countless challenges. The screen is more than just a display. It is the identity of the television, the very feature that defines the experience for viewers. Without the brilliance of modern display panels, the stories, colors, and emotions brought into homes through television would lose much of their magic. Creating a panel is not only about science, it is also about capturing the imagination, transforming raw glass into a portal that connects people to worlds far beyond their own. The first step takes place in a highly controlled clean room. The reason for this environment is simple. Any speck of dust or impurity could ruin an entire screen. Workers in specialized suits, resembling something out of a science fiction film, carefully handle sheets of glass that are destined to become the foundation of a television display. Glass is the largest single component of a flat screen and serves as the canvas upon which millions of tiny electronic miracles will soon be created. These screens are built by sandwiching together two thin sheets of glass. On one of them, a layer of silicon is deposited, and then begins a painstaking process of constructing millions of microscopic transistors. Each transistor will one day control a pixel on the screen, the tiny dot of light that forms part of the television's image. The scale of this construction is mind-boggling. To the naked eye, the glass may appear unchanged, but under magnification, one can see the vast network of transistors carefully etched across its surface. The process is repeated over and over until millions of individual cells are formed. Meanwhile, the second sheet of glass undergoes a transformation of its own. Here, a matrix of red, green, and blue subpixels, known as a color filter array, is created. Each pixel of the television is made up of these three subpixels, and by combining them in varying intensities, the screen can produce over 1 billion colors. The precision required is immense, because even a single faulty pixel could ruin the viewing experience. Once both sheets are ready, tiny amounts of liquid crystal material are inserted between them, and then the two sheets are bonded together. This delicate liquid crystal layer is what gives the display its name, allowing light to be controlled with extraordinary precision. However, liquid crystals cannot shine on their own. They need a source of light, and this is where LEDs come into play. The factory uses specialized machines to place rows of light-emitting diodes onto strips. The challenge is that the light from these tiny LEDs must be spread evenly across screens that can stretch more than 1.5 meters wide. The solution comes in the form of transparent plastic sheets known as plexiglass. Light entering one side of the sheet is scattered throughout its entire surface, creating a uniform glow. To enhance brightness and color, 2 additional optical films are carefully added, each engineered to boost the display's performance. At this point, the panel is ready to be framed. Injection molding machines produce strong plastic casings in various sizes, molded under high pressure to ensure durability and precision. These casings form the front and back frames of the television, giving structure to the otherwise delicate screen. Workers and robotic arms place the panel inside the frame, and slowly the television begins to take on its familiar shape. But a screen alone cannot make a television function. To bring it to life, a brain must be installed. This brain comes in the form of the main board, known as the SSB, and the power supply board, called the PSB. Both are manufactured right here in the factory. The SSB processes all of the television's data, running complex algorithms to ensure smooth images and clear sound. The PSB, meanwhile, regulates the electricity flowing through the device, ensuring that everything operates safely and efficiently. Other specialized boards are also installed, including control boards on the sides of the panel, a board for the remote control receiver, and even one for Wi-Fi connectivity. Creating these boards is a process of its own. Thousands of tiny components must be placed onto motherboards with precision. Machines work tirelessly, positioning each piece one by one, faster than the human eye can follow. Once assembled, the boards are run through a wave soldering machine, which electrically connects all the components in a single pass, ensuring a strong and reliable connection. Skilled workers then inspect and complete each board, preparing it to be mounted into the television body. As the assembly line moves forward, workers carefully screw the boards into the back covers of the televisions. Even here, precision is everything. The electric screwdrivers are carefully calibrated to apply just the right amount of torque, preventing any damage to the delicate components. Suspended from above, the tools are designed to reduce worker fatigue, ensuring consistency throughout long shifts. With the electronic brains in place, the televisions are almost ready to awaken. The next stop is the testing area, where each unit undergoes rigorous checks. Here, specialized machines load the necessary software and data into the television's memory. This allows the device to boot up for the very first time. Watching rows of brand new screens light up for their inaugural test is a remarkable sight. At this stage, each television is turned on vertically, allowing workers to perform visual and electronic inspections. Colors are tested, pixels are examined, and every component is checked for proper function. Highly sensitive scanners focus on key areas, detecting defects that the human eye might miss. A single inactive pixel is enough to disqualify a unit, as the factory's standards are uncompromising. The average lifespan of these modern displays is estimated at 100,000 hours. To put that in perspective, it means a television could run continuously for over 11 years before reaching the end of its life expectancy. Achieving such durability requires not just advanced materials, but also relentless quality control. High-definition screens contain more than 2 million pixels, each with 3 subpixels. Together, they are capable of displaying over 1 billion shades of color, creating the rich and lifelike images viewers expect. Before leaving the factory floor, each television endures a rigorous final quality control process. For a minimum of 4 hours, the screens are tested under different conditions, ensuring stability, brightness, and accuracy. Skilled experts oversee this stage, monitoring every detail to confirm that each television meets strict standards. Only after passing this final examination can a television be considered ready for the world beyond the factory walls. Once approved, the televisions are hand-packed into sturdy cardboard boxes. Each package is carefully designed to protect the device during transport with special inserts that prevent movement or shock. At the end of the assembly line, hundreds of boxed televisions are stacked onto pallets, forming towering columns of screens awaiting shipment. Trucks back into loading bays, and forklifts carry the pallets on board. From there, the televisions begin their journey, traveling across cities, countries, and continents until they reach the living rooms of eager customers. What began as fragile sheets of glass and tiny electronic parts has now become one of the most important devices of modern life. The journey from raw materials to finished product is one of precision, innovation, and teamwork on an enormous scale. Every step, from the delicate handling of liquid crystals to the powerful machines that mold casings and solder circuits, contributes to creating the vivid images that entertain, inform, and connect the world. Televisions may appear simple on the outside, just a screen mounted on a stand or hung on a wall. But inside lies a symphony of technology, perfected over decades of innovation. Factories like this one are the hidden engines behind the entertainment that millions enjoy every day. Each television carries within it not only the power of technology, but also the dedication of countless individuals who make sure every detail is flawless before it ever reaches a home. And with that, the story of how televisions are made reaches its conclusion. From sheets of glass to vibrant screens, from tiny circuits to breathtaking images, the process is a remarkable blend of science, engineering, and human skill. If this journey inside the world's biggest, imagine lining up every Duracell battery made in a single year. You'd wrap around the Earth more than twice. That's a mind-bending number of copper tops powering everything from remotes to smoke detectors. But how does Duracell actually pull off this insane pace of 10 billion batteries a year? Think about how invisible batteries are to us. They're everywhere. The remote you throw at the couch cushions, the flashlight you only remember when the power goes out, the smoke detector that suddenly starts chirping at 2 a.m. and makes you question every decision in life. We take them for granted until the moment they die, and then, suddenly, it's a crisis. Duracell has become the name people trust in those exact moments, partly because of that iconic copper top design, but mostly because for decades they've built a reputation for reliability. And yet, their story doesn't start with your TV remote or your kid's toy. It begins nearly a century ago and in a completely different world. Back in the 1920s, Samuel Rubin wasn't dreaming about AAs and AOAs sitting in blister packs. He was a scientist focused on developing better battery cells for specialized equipment. Alongside businessman Philip Rogers Mallory, they formed a company that at first made mercury batteries. And while mercury doesn't sound like the most user-friendly ingredient today, back then it was a breakthrough. These batteries became especially valuable during World War II, when the military needed cells that wouldn't give up in tropical humidity. The devices they powered had to keep running, no matter the climate, no matter the conditions. That reliability in the middle of war zones built the foundation for what would later become Duracell. The real shift happened in the 1960s. The company pivoted toward alkaline batteries, the kind you and I use every single day, and they needed a name that captured the promise: durable plus cell, Duracell. It was simple, but it was a promise. These little powerhouses would last longer than the competition. That brand identity solidified even further in 1973 when they rolled out the copper top design. Suddenly, you didn't even need to read the label to know it was a Duracell. It was sitting there in every grocery aisle, shiny and confident. That little bit of metal wasn't just branding, it was genius marketing that burned the image into consumers' heads. Ownership of the company bounced around over the years. First Kraft, then Gillette, then Procter & Gamble. Today, it's owned by Berkshire Hathaway. Yes, that means Warren Buffett, arguably the most famous investor alive, controls the batteries in your remote. You can almost picture him smiling every time you buy a 4-pack, knowing that even in the age of smartphones and high-tech gadgets, the humble AA battery still makes the world go round. So what actually makes up a Duracell battery? On paper, the recipe sounds like a science experiment that you'd probably fail in high school chemistry. Zinc, manganese dioxide, potassium hydroxide, graphite. Wrap that in steel, cap it with brass. Done. Except, of course, it's not nearly that simple. Zinc acts as the anode or negative terminal. Manganese dioxide is the cathode, the positive terminal. Potassium hydroxide is the electrolyte, the part that lets ions move back and forth. The outer casing is nickel-plated steel, tough enough to handle the chemical reactions inside while keeping everything sealed away. And that copper top? It's not just decoration. It's a nickel-plated brass cap designed to help conduct electricity cleanly into your device. Now, lots of companies could throw these materials together and call it a battery. But Duracell's entire reputation rests on the fact that they don't just toss stuff in a mixer and hope for the best. They use proprietary additives, precise formulas, and rigorous quality control that ensures consistency across billions of units. Every batch of raw materials gets tested before it even enters the production line. If the zinc isn't pure enough, if the manganese dioxide isn't up to spec, it doesn't make the cut. That's how they guarantee that whether you're buying a Duracell in Georgia, or in Belgium, or in China, it'll perform exactly as expected. And speaking of Georgia, Duracell's flagship factory in LaGrange is basically a cathedral of battery making. Imagine a production line moving so fast it pumps out 300 batteries every minute at each assembly station. Multiply that by multiple lines and you're looking at over 3,500 finished units per minute. It's like popcorn in the microwave, except instead of a snack, you get enough power to keep half the gadgets in your house alive. The process starts with preparing the cathode mix, which is basically a carefully engineered cocktail of manganese dioxide, carbon, and secret ingredients Duracell doesn't talk about. This mix is pressed into little rings or sleeves that form the outer portion of the battery's core. Meanwhile, zinc powder is prepared with its own additives to make it more conductive and less prone to corrosion. These two powerhouses, the anode and cathode, are kept apart by a separator, a thin paper-like material that lets ions pass but stops the two from directly touching. Think of it like putting up walls between roommates who really shouldn't be living together but still need to share the Wi-Fi. The steel casing, which will become the body of the battery, is formed and nickel-plated to fight corrosion. The copper tops are stamped out of brass sheets, polished, and set aside for later assembly. Then comes the moment when everything comes together. The cathode rings slide into the casing. The separator goes in next. The zinc mixture fills the center. A carefully measured amount of potassium hydroxide electrolyte is added. And finally, the copper top is attached, along with a plastic insulating washer to make sure the positive and negative sides don't accidentally connect. Sealing the unit is a critical step. Too loose and the battery could leak. Too tight and internal pressure could cause problems. Duracell has spent decades perfecting this process. Once sealed, the battery moves straight into testing. Unlike some rechargeable batteries that need forming, alkaline cells like Duracell's are ready to go as soon as they're built. But that doesn't mean they skip testing. Oh no. Every single one faces a gauntlet of checks that would make a Navy SEAL sweat. High-speed cameras look for visual defects. Automated systems measure voltage, resistance, and capacity. Samples from every batch are tortured with stress tests, extreme temperatures, accelerated aging, and leakage tests that simulate the worst conditions you could throw at them. One of Duracell's most important promises is that their batteries won't leak and destroy your expensive gadgets. That's why they put every unit through conditions harsher than anything you'd see in normal use. It's like training for the Olympics, just so the battery can live a quiet life inside your garage door opener. Packaging is another area where Duracell has flexed its muscles over the years. When they rolled out Duralock technology, promising a 10-year shelf life, it wasn't just a marketing slogan, it was a legit shift in how batteries were preserved. By sealing them more effectively, Duracell made it possible for people to toss a pack in a drawer and still expect it to work a decade later. That's not just chemistry doing the heavy lifting, it's smart packaging design working hand in hand with the product itself. And they didn't stop there. They added little power check features so you can actually test a battery before you put it in your device. It's like a sneak preview that saves you from the classic, "Is it the remote or the battery that's dead?" guessing game. For smaller coin-style batteries, Duracell went one step further and created child-resistant packaging. Anyone who's ever dealt with toddlers knows they'll try to put just about anything in their mouth, so making sure those shiny little discs are locked behind tough blister packs is a lifesaver. Literally. Sustainability plays a growing role too, and Duracell has been quietly reshaping how its products reach us. Over the years, they've cut down on excess packaging, ditched unnecessary plastic windows, shrunk the overall pack sizes, and boosted the amount of recycled material they use. Their philosophy is straightforward. When you're selling billions of packs every single year, even small changes add up to massive differences. Less plastic, less cardboard, less waste. It's a ripple effect that becomes a wave when you're operating at Duracell's scale. And it's not just what you see on the store shelf. Inside their factories, like the flagship plant in Georgia, they've taken sustainability just as seriously. That facility has committed to sending zero waste to landfills, which means everything is either reused, recycled, or repurposed. They've also slashed water usage by millions of gallons annually through efficiency upgrades, for a company that runs production lines day and night, cutting that much resource use is no small feat. These shifts might not be as flashy as the copper top design, but they matter, and they show that even in the world of disposable batteries, there's room for responsibility. Duracell isn't stopping at alkaline either. The copper top may be their superstar, but behind the scenes, they've been steadily building a lineup that covers just about every corner of modern life. They've got rechargeable batteries for people who hate running to the store every other week, ultra-tiny hearing aid batteries that pack a surprising punch, but sleek power banks that keep your phone alive when you're traveling, and of course, the Optimum line. That one's built for the gadgets that seem to inhale energy, high-drain devices like game controllers, motorized toys, and fancy flashlights, or for anyone who just wants their batteries to hang in there a little longer before giving up. What makes it impressive is how far the chemistry itself has come. The stuff inside today's Duracell cells is light years ahead of what you would have bought off the shelf even 10 years ago. They've squeezed out more power, stretched the shelf life, and made the whole package more reliable, all without changing the size. So your AA battery still looks like the same old AA battery, but it's been hitting the scientific gym behind the scenes. It's a little like upgrading your phone every few years, except your batteries keep evolving without forcing you to learn a new charging cable. They just keep slipping into the same remote slot, the same flashlight, the same controller, only now with extra endurance tucked inside. Now you might be thinking, this is all great, but it's still just a battery. Does it really matter? The answer is yes. In disaster zones, when the grid goes down, batteries keep radios alive, flashlights shining, and medical devices working. Duracell even has a rapid response program that delivers free batteries to areas hit by natural disasters. In developing regions where power grids are unreliable or non-existent, a simple battery might mean a child can study after dark, or a family can run a radio. That long shelf life suddenly isn't just a marketing feature, it's a lifeline. Economically, Duracell's global empire supports thousands of jobs directly and many more through supply chains. The factories not only power your gadgets, they power local communities. And that's part of why Duracell has managed to stay not just relevant, but dominant in an age when technology is constantly shifting. From its unlikely beginnings in the 1920s through military breakthroughs in the 40s to consumer dominance in the 70s, and now as a global powerhouse under Berkshire Hathaway, Duracell has built its name on one simple promise: reliable power. Billions of times a year, that promise gets fulfilled in devices all over the world. So the next time you pop a copper top into a smoke detector or shove a couple into a game controller, remember the journey it's been on. From carefully tested raw materials, through high-speed assembly lines, brutal quality control, and into packaging designed to keep it fresh for years. It's more than just a little cylinder of chemicals. It's 100 years of innovation squeezed into the palm of your hand. And if you enjoyed getting an inside look at how something so small makes such a big impact, don't forget to hit like, drop your thoughts in the comments, and subscribe for more stories like this.